Buenas tardes. Good afternoon, everyone. Welcome to the Center for Latin American Studies. I am its director, Professor Hector Hoyos, and it's my great pleasure to welcome you all here today. I'll be doing more of a ceremonial welcome and pass it on to one of our MA students to do the formal introduction of our speaker. We're very grateful that you could make it and that in this almost rainy afternoon you choose to be here with us. I will also note that Professor Barrera is here through the Tinker Foundation, so I'd like to thank the auspices of the Tinker Foundation. And just a general announcement, as I see that several of us work on Chile or are Chilean scholars, we are approaching the deadline of the Luxich Foundation application. And so if you know folks in any field really, and not necessarily from Santiago, but from everywhere in Chile, please encourage them to apply to Stanford through the Luxich Foundation. That's just a bit of an anuncio parroquial that had to be done. And then allow me to pass it on to Isa Calero, who will do the honors, please.
Hello everyone, my name is Isa. I'm one of the MA students here at class. It is my honor to present our speaker for today. Our speaker is Javier Barrera Martinez, who is an expert in applied probability. Her research interest combines stochastic processes, stochastic optimization, and reliable network design. She has contributed to the reliability network literature, developing new methods to design and evaluate reliable networks, incorporating geographical dependencies and failures. At the same time, she is interested in studying Markov models, abstract properties with reliable applications. Her research has been published in prestigious journals such as Mathematical Programming, Annals of Operations Research, IEEE Transactions and Reliabilities, and Annals of Applied Probability. Barrera holds a double PhD from the University of Paris Descartes and University of Chile. She has participated in research projects such as a RAREDEP, where researchers from Chile, Uruguay, Brazil, and France study the simulation of dependent failures using rare event techniques. She has also participated as a researcher in collaborative projects such as the operations research and energy and climate change, stochastic models of disordered and complex systems. She is permanently collaborating with female researchers in Chile and Latin America to communicate women's role in math and STEM research. She is currently an associate professor at Universidad Adolfo Ibáñez in Chile, where she teaches stochastic models courses for undergraduate and postgraduate students, and she has supervised more than 20 undergrad students, 7 postgraduate theses, and 1 postdoc. This quarter, we have the honor of having her here as a Tinker visiting professor, teaching the class Resilience and Reliable Network Design under the MS&E department. And today we have the pleasure of having her here to give the lecture, Power Systems and Telecommunication Networks Capable of Overcoming Disaster-Based Disruption. Thank you so much for being here with us today.
Thank you for this very nice introduction. I would like to thank the former director, Alberto Diaz, who made the invitation, Hector Hoyos and Elizabeth have received me, and Megan Sana Molly that have issued my first days here in Stanford. Of course, Jose Lecter, who sponsored my application. Okay. So I will talk about this disruption-based problems and I would like to share my concern, and also this is a problem that should be addressed from several different points of view. I will show you what I and my collaborators have added to solve this problem, but also I'm sure that from your field there's a lot to add to solve this problem and to raise the concerns. Okay.
We have the problem of having a talk with the title "Disaster-Based Disruptions." It's asking for it. You know? There we go.
Okay, so don't be afraid. I will be too insistent about the equations, but I will put them over there so I could fill the screen. Okay, so what are disaster-based disruptions and why I have focused in telecommunications, network, and power system? Okay, first, what are these disruptions? Disaster-based disruptions. So here we have a map that I generated yesterday. These are the earthquakes that has occurred during the last 5 years with magnitude 6 or more. Okay, so in Chile we're very used to talk about magnitudes of earthquakes. So as you can see, all these dots here are marking all the earthquakes. And here we have the more, with the greatest magnitude. And as you can see, Latin America is greatly affected by earthquakes. So if we consider the last 10 years and magnitudes of 7.5 or more, so here we have that you can see in the list of the top 10, we have Chile that appears twice, 3 times, Peru, Mexico. Okay, so I hope this doesn't discourage you of visiting my country. But so we need infrastructure that's prepared to overcome at least one big earthquake every 10 years. Okay, so to make a comparison from here, the intensity of how we perceive these earthquakes are more or less the same. This is a measure of the energy that is released. So the energy of the earthquake that we perceive is higher, but it's deeper. So we perceive something similar, but the area that is affected is bigger for these magnitudes. Okay. This is an ice storm. This is a photograph of the province of Chubut in Argentina, in the south. Everything is in the south, very in the south. And this is a transmission tower. It has collapsed here. So this occurred, and the output of energy was enormous. They had to buy a lot of electricity to Brazil, and we're thinking of adding more imports from Uruguay and Chile. So this shows that this is not something that each country has to deal with it by itself. It's something that we need to deal together. Okay. This is a volcanic eruption of the Calbuco volcano. This is a photograph from the city of Puerto Montt, and occurred in 2015, and the damage were enormous to health and economic activity. There's a lot of tourism and cultivates that are here that were affected, and the problem was so big that the ashes traveled 940 miles from Calbuco to Buenos Aires and affected the health even from Buenos Aires people. Okay. So, how this affect the networks? Well, here we see it's not that easy, but here we have components that are in the floor that are from the damages generated by the 2010 earthquake that cut almost half of the country went without electricity in that moment for an important period of time. Here we have something in California. The fires also will affect them. And we have here a typhoon that affected the Philippines, and also all that affected the energy distribution. Okay. So this is a a very costly problem for us. This is a study that was made just after 2020 earthquake. For us, this is reached like almost 1.2 of our GDP, so that's a lot. But also it's very important for other countries like Colombia and Mexico. You see that that's very important. So it is reasonable to think that we can invest a lot of money in improving and preventing these problems, rather to reacting and solving after the disasters. Okay. So how do we decide to build power systems and telecommunication networks? So the more classic criteria, and the one is used today to build, is that the system must need to stand even if one or two components fail. Let's call the N-1 or N-K criteria. There are some others that look at how important are some components and then make those decisions, but this one is the more popular criteria. Okay, but these criteria focus on typical failures, not on disaster-based failure. So, or other way to put this is if our electric and telecommunications infrastructure was built years ago, and these original criteria have stand many natural disasters. Okay? Why we must question these criteria's failure today? Well, as you can see, if you make a memory, 10 years ago we didn't use as much the internet to perform our activities. Okay, and also there's more of these activities that need also the electricity. Okay, we are in a race to diminish the CO2 emissions, and we are replacing our natural gas and gasoline consumption with electricity. So this will lead to over-concentrate our risk. So now when we don't have electricity, years before we could continue to drive our cars and cooking or heating, but now we won't be able to do anything. That's what I mean by over-concentration the risk. And then that leads that we need a higher standard for our networks. Okay? And also, on the other side, climate change is incrementing the chances of certain natural disasters, like wildfires, bad floods, and this also cause dependent failures. Okay. So this report is very interesting, with an analysis done of electrical for power systems outage in the state, but is valid for many other countries. And so what is a typical failure and what is an outage, or typical outage and outage due to natural disaster? So in typical outage, we have failures that are isolated. When we say there's not spatio-temporal correlation, means that it's highly improbable that if one component failed here, it's other that fell near. Okay, so they are isolated mainly. Okay, and they are quick to repair. And here, to repair. Okay. But when we have a natural disaster, we don't only have one fault in the area. We have multiple faults in the area. So this means that there's a correlation or dependence from the geographical location of the failures. And also, it's not only this infrastructure that failed, not only the telecommunication network that failed, it's also that the power system failed, also the highways, the network composed by the highways are also failed. So this means that it's more difficult to repair or restore the failures because we cannot travel easily, we cannot coordinate with communication to solve the problems. And in a very practical example of this, in 2010, when occurred this big earthquake in Chile, people told that they didn't have cash to go and buy the gasoline to put on the cars to get to repair the infrastructure because they were not working, okay? Because they didn't have electricity. So you see that's it's a problem that it will increase with these simultaneous failures. Okay. Also, here we have a list of several disasters, and here is the mean size and the number of customers that were affected. So, although we have that hurricanes and ice storms are more frequently, earthquakes affect almost the same people that ice storms, and over here we can see if we can prepare, and earthquakes are almost unpredictable. Okay, so it's for example the wildfires we can prepare this coming summer and we can prepare some things, but for earthquake we must be every day prepared. Okay, so we need a couple of concepts to decide if this network will stand or not the failures. So there's two concepts known: the reliability and resilience. The reliability is the ability of an item to perform a required function under given environmental and operational conditions for a set period of time. The resilience is as a concept that is used widely in the literature with different meanings in different domains, but in general it means that we have the capability of a system or even to a society to absorb and adapt to a disruptive event and recovery from this event. Okay, these concepts are linked to the risk hazard because it's not a problem that we have an earthquake. It's not a problem that we have an ice storm. It's the problem that there's a very bad consequence because of where we have chosen to live to construct our infrastructure. Okay, so this is the we will not be worried about this if not there's a risk hazard associated with it. Okay, so telecommunication network. I will show you a work that we did in collaboration with Dora Jimenez, excuse me. This is her PhD work, and with Dr. Cancela. Okay. So I'm focusing on optical networks. This is the optical network in Mexico. This is the one in Chile. It's very beautiful. And these optical fibers are when we connect and here travel the information through light pulse. Okay, like travel over here. Okay, and this is these networks in each country are connected to the other countries through these other networks. Maybe they go through the sea. Okay. So when we are in a country, we will consider a very simple model where we have, for a city, we have a building where we are receiving all the communication of the city and we'll send it through these optical fibers to other cities. Okay, so we have buildings and we have optical fiber cables. So if you live here, you have perceived some earthquake and the movement will cause damages in the infrastructure, like these two buildings that are here. And what is less known is that they also cause damage in the optical fiber. So here we have some very nice report done in New Zealand, where here we have a bent optical fiber, okay, and here is the optical fiber is cut, so it's not going there, and it's because of these cracks that can generate in the earth that this is produced. So how do we study how these problems get? So there's something called the probabilistic seismic hazard analysis, and it has 3 stages. The first part is that we need a seismic source, where and with what energy this seismic occur. Okay. Then we have the given a building that is a certain place, it will perceive it with a certain the movement will be perceived at a certain intensity. Okay, so from this information, we generate the ground motion prediction equation. With the ground motion prediction equation, we generate the intensity measure at each location. Then, with the intensity measure, there's a building that will perceive this movement and will generate a level of damage. Okay, but the better the infrastructure or better prepared for earthquake is less likely to be damaged. So, so for the first part, what we did was to take historical data of earthquake, and we changed the magnitude to magnitude 8. As you saw, in 10 years in Chile, it's very usual to have 1 or 2 earthquakes of that magnitude. Then, what is in the second stage, when we have a location for the earthquake, so this is under the level of the earth here. We have that here they will perceive the movement. So here's what is near the source, so it's a bigger intensity, and here will be a smaller intensity. And this also will affect the optical fiber. Okay. Here are some equations. These equations are generally calibrated for each country. So there's a long list of equations. And when we have this is the optical fiber, so the cable, we divide the cable in several portions, and each portion will perceive also a movement that will be less intense if you are farther from the source and more intense if you are near the source. And there's also different quality for the cables, and also the terrain characteristic will affect if this will break or not. Okay, this is a very new model. Was recently proposed in 2022. Was in parallel as we were making our research to develop this analysis. And then what we do is simply we take the network, we simulate several earthquakes, and we check what arcs and links are unavailable, and then we say, well, for all these links or for all these scenarios, they're not available. The network is not working, and for all these scenarios, is this working? And we take an average. Okay, we have 2 criteria. One is that one source and terminal node are connected, and the other one is that we need that aside of being connected, we need that the number of links that you need to travel to get from one node to another is not bigger than a certain number. And this is because now we have on-time communication. And for doing this, if communication will degrade too much if you have too many hubs. So this criteria is good for sending mails or sending photographs. This is for doing what's assumed activity. Okay. So this is Chile in South America, and we study. This is not the complete network. This is another network called REUNA that connects the main research centers in Chile, and it is an optical network, and we study how it was affected with this model. This is more schematic, but because as you can see, it's so long that it's better to bend it a little bit. And these links over here are proposed extension, and this is a 4th link proposed to extend. So we study models with 3 links extensions and some with 4 links extension. Okay, and here, well, we did 10,000 simulations average, and we can see which models produce a better reliability or improve the reliability from the first design. Okay, so allowing us to choose. Okay. It was important also to check how was this performance if original source and terminal nodes were far apart. So it's degraded very quickly, the level of reliability. So here, for example, for nodes that are less than 250 kilometers apart, we have near 90% of probability of being connected. But when we go to those that are more than 200,000 kilometers apart, the degradation is very fast. And for the diameter constraint reliability, that is that we need a minimum of links, a maximum of links to be apart, it can be very, very bad. Okay, but still improves a lot from the original reliability of the model. Okay. Okay, so I don't want to get too intense for the numbers. So what we prove or state is that we can do it. We can understand how they work, how we can improve the reliability of a network that should stand earthquakes, and that we have the models. Still, there's some work to do because we're dealing with events that are not that frequent. Also, that we need a lot of information. Even today, we don't know exactly where all the optical fibers are located. And if we don't know where are located, we cannot estimate what is the probability to have a disruption. And that we can, the other important thing is that we can capture the geographical things. And afterwards, what we want to do is this network not only has to stand earthquakes, but it's the same network that has to stand mud flows, volcanoes, and everything. So we have to complete with all the other natural disasters that are can affect. So for power system, this is work that we did with master thesis with Limbopi and other colleagues. And this is what we did in this study is this is a small portion of Chile in the north. This is Antofagasta, and we put here a network that is artificial. This is not actually what is there. So this is a classic example of networks. And these dots that you see here are the epicenter of different earthquakes that are actually occurring in the area. Okay, and we force that all these earthquakes will be of intensity 8, and we all the links that are in yellow are proposed links that we might construct. Okay, and those that are in black, they are already constructed. Okay. So here we have another equation, and so again we have a source, and we have the substations that provide energy to the cities that can be affected, and here we have that the transmission towers can be affected with the earthquake. Okay, and if the movement is too much, they will fail according to some time fragility equation, and we will say that a transmission line will fail if one tower fails. Okay. So here we compare how the model we obtain, the more cost-efficient model, if we compare with the N-1 criteria and a model that considers all the possible outcomes with these earthquakes. And the lines in yellow are that finally construct, and here you see those two models are very different. We're constructing very different things. Okay, this is another alternative that is also popular in the literature, but I will mention it. And something very important is that don't look exactly the numbers, but here this is when we consider the earthquakes. Here's a total cost, and this is the investment. So the money that invests on the lines, the money we invest to generate, and the money that we pay for energy that's not provided. And if you can see, here is a lot cheaper from the point of view of the investment, and also we have less loss load. Okay? So it's really, although it's not a big difference here, it is important that it has less energy not provided at the same price, more or less. Okay, so when the right set of probabilities is used, we obtain a completely different configuration of the network, and also we obtain a lower expected cost and even more less energy not provided. And this is basically because we here have the probability. This is the related difference. I don't want to explain exactly what it is, but what I'm saying in this graph is to compare what if they were independent versus what happens in reality. And the thing is that the probability that two arcs or two substations fail simultaneously is 50 times bigger than if I assume they were independent. Or they mostly, I think, we have isolated the failures. So it's really important to consider that failures will occur at the same time. So for ice storm, we did some study in a master thesis, and we got to several conclusions. Here, what happens, and what's happening in the pictures that I show you of Argentina, is that in an ice storm, there's some special condition where there's a combination of a special, it's not snow, special ice that get cut into the cables and in the tower. It's se adhiere, I don't know if in English. And also there's the wind. So you start with the cable like it's like this finger of size, and afterwards you get with something like this size. So the cable comes of this size, and the design for these towers and these cables, they think, well, this tower must stand some wind or some weight, okay? And the same for the cables, but it's actually the combination of both that make these failures to occur, okay? So we have also an interesting method that allows us to simulate these ice storms and that weather effect. But and we can see, okay, that's two limitations. Okay, so we did some simulation for this. Is in the south of Chile, in the city of Concepcion, that has a position similar to San Francisco. There's the mountains, and again we have that the probabilities to fail independently, and that compared to fail simultaneously, we have 12 times up to 12 times bigger than if we assume independence. Okay, and this criteria, as I told you, ignore it. So the problems that we have to overcome to do this study is that there's a lot of missing information. There's information in the urban areas because building, in the case of earthquake, building infrastructure that is resistant to earthquakes is something that we have done, I don't know, 50 years. But this information is available in the cities, in the urban areas. When we go outside, we don't have this information. We don't have where the cables are, and we need this. And maybe somebody can argue that they are very expensive to obtain, but actually we don't need something as precise as we need to a building. So something with some analysis of images can be done to obtain something roughly. There's already some results in that area, and that will be not that expensive to obtain. Also, in the context of the power transmission work I show you, we have a big discussions about the cost. How do we put the cost for the energy not provided? And it's not the money that the company has to pay us, but no, for not providing the energy. There's a lot to do there, because the fact that simultaneously it's a big region that don't have energy is a lot worse. So hospital cannot send our operation that must be delayed, can send it to another place. There's a lot more requirement of the people that are being affected by the natural disaster that are needed. So the costs are bigger, and we need to understand how this will affect the different places, and the rural places. It will be particularly important. For example, today we have in Chile a list of electro-dependent persons. So these persons that need a machine to live, and if they don't have electricity, they will die. And so we need to respond to these people timely. Okay. Also, there's a infrastructure dependence. I didn't show, but we have a study where the same Reuna network is also we consider so it's dependent of the power system. Okay, so usually for the telecommunication area, you will have batteries, but these batteries are, I think, for typical failures, and they usually will last 6 hours. But in a situation like this, after 6 hours, you will not have reparation. So the system will degrade more performance, not because of that a component has failed, it's because it doesn't have energy to work. Okay. And finally, there's other challenge, because there's only one network that we design, and it has to stand at the same time tsunamis, wildfire, earthquake, mud floods, volcano eruptions. So it should be something that consider all things at the same time. And there are very few studies that are thinking of simultaneous these problems at the same time. Okay. So that's my talk.
The floor is open for questions.
We have a question from Professor Thomas O'Keefe. He would like to know, what would be an example or examples of enhanced resilience to climate-exacerbated natural disasters in small island developing states, whether in terms of electricity or telecommunication?
Well, it depends which are the menace they have, but something naturally occurs that these menace are geographically located. Okay, so we have something that you can relate to finance, that we have to diversify the risk. So if we have more than one way to communicate or send our energy between places, it will improve. My intuition, because I haven't proved it, my intuition is that will be useful for all these natural disasters, because they tend to be all in the same place. I hope it's enough for him. Or her.
I'll let you know if it makes sense. Thank you.
I'm wondering if you're doing any work while you're here at Stanford with, I think it's Professor Holberg, who's using fiber optic cables to track underwater earthquakes, which seems quite similar to the work you're doing of using optic cables in relation to earthquakes.
Oh, that would be very interesting. I wasn't aware of that, and actually it was a point that we talked to meteorologists and oceanographic people to understand how tsunamis, not necessarily the earthquake, but tsunamis will affect the optical fibers that are in the sea. But we couldn't find a model that we can simulate. We only have some guidance of how they think they could occur. Okay? But it would be great to know if they are doing something. So I will ask you for the information.
I don't know him. I just knew someone who was working with him.
It's a lead.
Just one question.
Yes.
Thanks very much for the nice talk, Javiera. Those models, the ones that are developed in 2022, 21, are these models calibrated to the disasters, future disasters, as in kind of climate is changing, and so the models might be changing. Is that something that is included in the development of those models?
Well, I haven't worked with this, but it's actually a concern because, for example, the norms are at least state in Chile for the functioning of the electricity networks. The state that you have to be able to stand like something like about the last 50 years start. So the last 50 years, about all the rain that you have to produce energy, you consider that, and also things that occurred during the last 50 years. And that's not what will happen in the future because of this climate change. And there's a lot of news that are telling that we have this challenging arising, and I haven't read something that has deal with the new rates that these things will occur.
Follow up.
Mm-hmm.
So is the regulation states that you have to withstand the last 50 years of disasters in the region of interest? Like, say, for example, I want to test the reliability of the network in some region in Chile. Do I look at the whole history of events that are disasters in the whole country, or only on that network?
Well, it's only about the energy you can produce and the water you can have. So you have to, because if there's no rain, in Chile mainly, if you don't have water, you can almost not produce electricity. So this is changing a little bit now with solar energy, but so the law where it says that you need to prepare to those climate events that are related to water. There's not a regulation. There's a regulation of how you have to construct. There's to build that to be support to stand earthquakes. But there's not related about with the energy that you will provide.
Because of earthquake,
Exactly.
Just because of water-related events.
Yes.
But even the water-related events could be like there are big storms in the south, but not in the north.
Mm-hmm.
So let's say I'm interested in the north part of the country, and I want to test my design, my reliability design, involving events. Currently I suppose they don't use events that are in the south, because they would say, well, there is no snow. But if they were to use that, they probably will be safe, because what is happening is that this polar climate is actually moving north, right? So that would be one way of actually making it resilient, even if you didn't have historically.
Uh-huh. Yeah, well, for us, it's more or less the contrary. We have more dry climate, and so the snow is going more to the south, and we have less water. But yeah, one problem is that we should consider the rates of occurrence of these events that are coming, and not the history. That's what you're saying. But there's no regulation about that.
Thank you very much. I have a couple of questions, and I appreciate that we have had some granular questions, because I'm going to go a lateral move.
Mm-hmm.
So one has to do with, and first I should preface by saying I find infrastructure as a humanist a very interesting topic of conversation. I think we neglect it often, at least in the humanities. We think about superstructure, social structure, less so about infrastructure, right? Literally undergirds everything that we do. There's a paper by Brian Larkin called The Poetics of Infrastructure that if you haven't come across it, I recommend. It discusses how infrastructure, and he talks about the train, is part of a sensing of modernity. So how we feel modern or we experience modernity has to do with infrastructure. So there's all kinds of ramifications for an interdisciplinary program as the Center for Latin American Studies. My questions though have to do with feasibility.
Mm-hmm.
I'm thinking of Fukushima, and my very naive impression is, oh my goodness, if Japan couldn't prevent it, then how can Chile? And I say this with great esteem for the country. So I'd love to hear more about feasibility, and also a very lateral question, just based on your expertise. I'd be curious to hear your thoughts about Cinco, or Cyber Sin.
Sorry, what's the last word?
Cinco, Proyecto Cinco, or Cyber Sin. And if you don't know of this, that would be really interesting as well. This is the project that Unidad Popular from 1970 to 1973 had for a cybernetic network in all of Chile. And there was recently at La Moneda an exhibit based on Eden Medina's work. Eden Medina, who's a great STS scholar based at MIT. But the conceit of Cinco that obviously didn't come to happen was that the country would have been connected cybernetically, right? And there would have been reports on crop production and labor dynamics that would allow a centrally planned economy to make decisions on the spot. And the science is quite there. Don't take it from me, take it from the NMA. So anyways, just two lateral questions maybe about feasibility and if applicable at all about CyberSyn.
So the network in Chile is very good to transfer information. And also there's this other network that it's between the research centers. So I think it's not a problem. Well, you have to take decisions in the moment. And I'm talking about preventing things or to be prepared for. Okay, and I think an issue that is very that I didn't mention, but it's very important from the more broad point of view is the who owns the networks are this telecommunication company or these energy companies. In particular, in Chile, Movistar is in Spain, and it is from Italy. But the people who pays for the problems that arise from these interruptions usually are the people and the government. So there's a deal that must be done because the money is there. So that's what we are saying. You can build more reliable networks if you consider this cost that you will incur afterwards. But you have to make a deal in where that in some way this investment should be done by the owners of this infrastructure so that everybody will win and not pay for these problems. And that also pass through establishing very accurately what will be the problems. And this is a multidimensional thing to address. So And I don't know if I answer your question or raise address your point, but I think it's go over there.
So the infrastructure is privately owned. There are stockholders of global north companies that get dividends from the fact that there is infrastructure in Chile.
Yeah.
Just asking.
Yes. I am interested in about 2 questions about the field. So first of all, like how did you get interested in it? And then how do you see this field of study has changed in the past 10 years? And how do you foresee it, shape and develop a decade from now?
Thank you for your question. I started as a theoretical mathematician, and my interest is in modeling the randomness. Okay, but also was highly motivated by applied things. And when I studied in France, when I went back to Chile, I got to an engineering school, and there was students needed to do applied projects. And there was this students that have this project in telecommunications. So I started to see, and I saw that there are a lot of probability tools that are applied in that setting. And I got curious to understand how this network work and how they apply these models called Markov chains. And when I started looking, I saw that there was a lot this assumption that the probability that 2 things fail at the same time is negligible. Okay, and say, well, it's not that difficult to address when these things fed together. I started to look at it and saw that there was a big opportunity there, because this is a question important to solve today, as I showed at the beginning of the talk. And I think more or less we have the tools. Some of them we are developing, but in the modeling part and the algorithmic part to solve those issues, we are getting there. Okay, there's a lot that is missing. Is information of as I told, of the cost of where the affected persons are and how they are affected by this. Okay, so there's a lot of progress to do over there, because it won't matter if we have the models and we have the computational capability to solve them if we don't have the information to calibrate them and solve them. Okay? And there's a lot to lose in the game for everybody. So we'll make the wrong investment, people will get affected, and historically it's a known fact that if you build something and you have to fix it to match certain necessity, it's a lot more expensive than if you construct it from the beginning to deal with that. Okay, so we are in that moment. We will be extending telecommunication networks, and we will be extending power system in the following years, and we need to do it right.
Sorry, that made me think of Haiti as an example of where we really failed. And if we have the tools, where do we start with a place like Haiti, where building codes haven't been followed, so whenever there's an earthquake, the damage is even more. The effects are exacerbated because of poor infrastructure and not having the government capabilities to make those changes. So what do you do in that case?
Can you repeat the question or rephrase it, please?
IT.
Huh?
El caso de Haití.
Oh, in IT. In the earthquakes?
Yeah, with infrastructure in a place that doesn't have the tools or the physical ability to make changes. How would we stop disasters from being so disastrous?
Well, there's an area of engineering that's called I don't know exactly the name in this moment, but it's logistic for natural disasters, for disasters. Okay, and there's a lot of knowledge from engineering that can be applied in that situation. So I saw an expert in this area that actually mentioned this power in IT, and so what do you do to take the resources to the people they need if there's no mayor to contact? Okay,
Right.
so this is not from my area, but I think I answered this question for you. So it's important to contribute to the local organizations. It's very important to, there's, for example, church that are organized. It doesn't matter if you're of that religion or not. They are organized and they know the people and they can give the support more. Not to only one person, so to all the people out there they need. They're also important and how things, there's something called the minister chain and supply a lot for all the industry, but it's one designed for these situations and how do you have to send things. And it's very usual that you say, we need clothes or we need water. And after it's come a lot of water and you spend a lot of money transporting something that you don't need. So you have to address that and define the exact quantities and define how this will go to don't see those things that are called the whip effects, that you will ask for something will come in amount that you don't need. Okay, and so there's some things to do there, and I'll also link to these disasters. But it's also important to have before which are the institutions that are there, what other people you have to contact. So all that information is necessary to have it beforehand.
I'm looking at the clock, and I want to suggest we adjourn, and thank you very much, Javi.
Thank you very much.